What would you do if your kid was very curious about little fish? To avoid all their questions, you might buy them a fish tank. Bring home a small slice of the vast ocean that they can learn from on their own. But what if they're curious about the vast empty space in our universe? It turns out that there are some secrets hidden within the vacuum that makes up most of our universe. So wouldn't it be nice if you could bring home a slice of intergalactic space? Well, a bunch of these curious kids grew up and became scientists that built magnificent tools to learn about our universe from within a laboratory. Like lasers that can make a short flash of light stronger than the average power of sunlight across 200 billion football fields, focused to a spot as wide as your hair. And these lasers can help safely replicate the extreme conditions of outer space inside a lab. But using these lasers in a precise manner to study fundamental properties of the vacuum has a couple of problems. Number one, we need to know exactly how strong the laser is when it is focused to a spot so intense that no material can survive. Number two, we need a near perfect vacuum when there is no way to remove every single particle from within a box. To tackle these problems, I study how tiny particles called electrons move under the influence of the world's most powerful lasers. I evacuate as many atoms and molecules as possible from a chamber and focus a laser to a spot that rips out electrons from these remaining atoms. And I showed that for increasing laser intensity, these electrons are ejected from the laser focus closer and closer to the direction in which light travels. So we can find out how strong the laser is by measuring the ejection angle of these electrons. We also found that imaging these electrons shows us how well the laser is focused when we cannot directly stick a detector in that intense spot. Now, getting rid of the electrons still gives us a cleaner environment to study the vacuum, even if we can't get rid of all the particles. So I used a second laser pulse to see how well these electrons are cleared by the leading laser pulse. Sort of like shooting two cue balls on a pool table. One to clear and another to see what was left behind. I found out how long it takes to create a less cluttered environment for vacuum-based experiments. And these findings play a crucial role in allowing us to harness the world's most powerful lasers for a variety of phenomena, from revealing the secrets hidden in empty space to enabling fusion energy and radiation therapy. But it is my hope that someday I can help you answer all the curious questions that your kids may have, thanks to the fish tank of the universe that we can make in our laboratories.